Hello everyone, welcome to yet another session on learning about Ethereum. In this session, we'll showcase real-world examples of gas optimization techniques used by Ethereum developers. You will learn about strategies to minimize gas costs and enhance the efficiency of smart contracts on the Ethereum virtual machine, that is, the EVM. By studying successful optimizations, you will gain valuable insights for your own projects. Moving on to the next slide. The importance of case studies. Case studies offer practical insights into applying gas optimization techniques in real-world scenarios. They help developers understand challenges faced and innovative solutions implemented for optimal performance on the EVM. By analyzing detailed examples, engineers can grasp the trade-offs and decision-making process in optimizing smart contract code for gas efficiency. Moving on. Here is the first case study, that is optimizing storage writes. This case study focuses on reducing storage writes, the most expensive gas operation. By analyzing contract logic and data structures, the team identified opportunities to batch and catch writes, significantly lowering gas consumption. Key steps include understanding storage usage patterns, implementing batching techniques, measuring gas savings, and sharing insights with other developers. Moving on. Here is the initial contract code. The initial version of the contract frequently writes to storage, leading to high gas cost. The high gas storage contract updates the stored variable every time the set function is called. This simple contract design, while functional, does not take into account the significant gas expenditure associated with storage operations on the Ethereum virtual machine. In the upcoming case studies, we'll explore techniques to reduce storage writes and minimize overall gas consumptions in smart contracts. By analyzing the contract's logic and data structures, developers can identify opportunities to batch and catch writes, leading to significant gas savings. Moving on, here is the optimized contract code. The optimized version of the contract reduces unnecessary storage writes by adding a conditional check. In this improved code, the storage variable is only updated if the new value is different from the current value, minimizing the number of write operations to the Ethereum virtual machine and resulting in significant gas savings. As you can see, if only the value of the stored data is changed, then only the value is updated when the set function is called. With this approach, careful analysis of the contract's logic and data structures can lead to tangible improvements in efficiency and cost effectiveness. Moving on, the gas saving analysis. The optimized contract demonstrates a significant gas savings by reducing unnecessary storage writes. This emphasizes the importance of minimizing storage operations for gas optimization. As storage is costly on the EVM, developers should address inefficient storage usage to achieve measurable gas savings, which can justify the effort spent on optimization. Moving on to the next slide, that is the case study 2, efficient data structures. In our second case study, we'll see how by using mappings and struct instead of arrays, we can optimize gas consumption on the EVM. By analyzing data requirements and access patterns, we replace arrays with more cost-effective data structures, achieving significant gas savings as the gas spent is very costly. Developers must balance the flexibility of arrays with the gas efficiency of mappings and structs. While arrays are easy to use, they can be costly for operations like iteration and insertion. Mappings and struct offer target and efficient storage but require careful planning and implementation. Here is the initial contract code. The initial version of the contract uses an array to store balances, which is inefficient on the EVM. By storing balances in an array, the high gas array contract must iterate through the entire array to find a specific user's balance or update the balance. Each time the add balance function is called, which uses an input amount, the balance is pushed into the balances array. This approach can lead to high gas cost, especially as the number of users or balance grows. Ethereum developers must carefully consider the trade-offs between the flexibility of arrays and the gas efficiency of the alternative data structures like mapping and structs when designing smart contracts. Moving on, here is the optimized contract code. The optimized version of the contract uses a mapping instead of an array for more efficient data storage. Mappings provide constant time complexity for lookups and updates. By replacing the array with a mapping, the contract can perform balance updates and lookups at a lower cost on the EVM. The efficient mapping contract demonstrates the optimization by storing user balances in a mapping instead of an array. The update balance function takes two inputs, that is, the address of the account and the amount to that specified address, and it simply sets the balance for a given Ethereum account without the need to iterate through an entire array. This targeted approach results in significant gas savings compared to the previous array-based implementation. Moving on. Here is the gas saving analysis of this particular case study. Using mappings instead of arrays dramatically reduce gas and usage for lookups and updates, as mappings provide constant time access while arrays require constantly iteration. This example highlights how switching to the right data structure can lead to a significant cost savings for decentralized applications on the EVM. Moving on, we have the case study 3, that is based on batch processing. Our third case study focuses on batch processing. Processing multiple operations in a single transaction can be more gas efficient than performing each operation separately. By grouping similar tasks together, developers can leverage the economies of scale and reduce the overall gas consumption of the decentralized application. Here, we'll identify opportunities to batch related contract calls and updates and implement efficient batch processing logic to minimize the number of storage writes and other costly operations. Also, we'll measure the gas savings achieved through batch processing and compare to the initial non-batched implementation. Moving on to the example. Here is the initial contract code. The initial version of the contract, individual processing, processes transactions one by one, updating balances for individual Ethereum accounts. This approach, while straightforward, leads to higher gas costs due to repeated transactions overhead on the EVM. Each balance update requires a separate storage write operation which can quickly add up as the number of transactions increases, resulting in suboptimal gas efficiency for the decentralized application. By processing transactions individually, the contract misses opportunities to leverage batch processing and other optimization techniques that could reduce the overall gas consumption. Developers must carefully analyze the contract's logic and identify ways to group related operations together, minimizing the number of costly storage writes and other EVM operations. Moving on to the optimal version of this code. The optimized version of the contract processes multiple updates in a single function call. The batch processing contract uses a batch update function that takes in an array of Ethereum account and an array of corresponding balance amounts. This batch processing approach reduces the overhead of repeated transactions, leading to significant gas savings compared to updating balances individually. Here, we don't retrieve the public storage variable balances every time we have to store up amount to a particular account. By grouping related operations together, the contract can leverage the economies of scale and reduce the overall gas consumption on the EVM. Instead of performing a separate storage write for each balance update, the optimized contract can execute all the updates in a single function call, minimizing the number of costly EVM operations and reducing the gas cost. Moving on, we have here is the gas saving analysis of the third case study. By processing multiple updates in a single transaction, the optimized contract significantly reduces gas costs compared to initial implementation. This batch processing approach minimizes the overhead of repeated transactions on the Ethereum virtual machine by reducing costly storage writes. Instead of separate writes for each balance update, all updates are executed in a functional call, substantially lowering overall gas consumption for the decentralized application. Moving on, we have the case study 4, that is leveraging off-chain computation. In the fourth case study, we explore how leveraging off-chain computation can optimize gas usage in Ethereum smart contracts. By offloading complex calculations and data-intensive operations to off-chain processes, we significantly reduce the on-chain gas consumption. Resource-intensive tasks such as complex mathematical operations, data analytics, or machine learning algorithms can quickly exhaust the gas limit on the EVM. Moving these computations off-chain minimizes costly EVM operations, enhancing the overall gas efficiency of our smart contracts. Here is the initial contract code. The initial version of the contract, on-chain computation, performs complex calculation directly on the EVM. This function takes two input parameters A and B and calculates their product and then divides the result by 2. The on-chain computation can lead to high gas cost as the EVM is not optimized for performing resource-intensive mathematical operations. Developers must carefully analyze the contract's logic and identify ways to minimize the number of costly EVM operations, especially for tasks that are not directly tied to the core functionality of the decentralized application. Moving on, the optimized version of the contract performs the computation off-chain and stores the result on-chain. By moving the resource-intensive calculations of the EVM, the off-chain computation contract can significantly reduce the overall gas usage of the decentralized application. This contract's store result function stores pre-computed results on the blockchain, eliminating the need for the EVM to perform complex calculations. This approach leverages off-chain computation using more powerful hardware and specialized algorithms while maintaining the security and transparency of the Ethereum network by recording the final result on-chain using the store result function. On the screen, we have the gas savings analysis of the fourth case study. By offloading complex computation to off-chain processes, the optimized contract drastically reduces gas usage for on-chain operations. Instead of burdening the EVM with resource-intensive tasks, it delegates these to more powerful off-chain systems. This results in gas savings, which enhances the cost efficiency and scalability of the decentralized application, making it more accessible to a wide user base. This approach uses external infrastructure like cloud computing or specialized hardware to perform complex operations without excessive gas consumption. Moving on to the conclusion slide, that is strategies for gas optimization. The case study highlights effective strategies for gas optimization in Ethereum smart contracts, such as minimizing storage writes, leveraging efficient data structures, implementing batch processing, and offloading complex computations to off-chain systems. By carefully analyzing the contract logic and implementing appropriate strategies, developers can create effective and scalable smart contracts, making Ethereum solution more accessible to a wider user base. Moving on to the final slide, before we wrap up, here are some questions to consider. Which optimization techniques have you found most effective in your Ethereum smart contract projects? How can you apply the gas optimization strategies discussed in these case studies to your own contracts? The key is to carefully analyze your contract's logic, identify opportunities for improvement, and implement the appropriate techniques to achieve the desired gas savings. We encourage you to share your thoughts, questions, and experiences in the discussion forum. This collaborative exchange will help the community further advance the state of gas optimization practices on the Ethereum network. Thank you.